Hello, here's a couple of problems that involve mass distributions. The first one is two masses. One of them is the mass along this axis here. Let's call this the y-axis. And we have this mass in the shape of a uniform rod of mass m. And then you have a second mass along the y-axis, let's say here, call it little m. Let's say little m is x away from the first mass, and this rod is of length L, okay? Don't worry about the other axes. It's all around along the y direction. So what will be the gravitational potential energy at the potential energy of the system, let's say, okay? The gravitational potential energy here, find it. Okay, now the thing is, the formula you know, which is negative G m1 times m2 over r. Imagine this was maybe a satellite going around the Earth and all that. Well, we assumed a certain symmetry. First of all, Earth was almost like a point particle, or spherically symmetric, okay? Which means the same thing, because you can always shrink the object to the center. And you had the satellite like a point particle. In this case, though, we don't have such symmetry. And X and L are comparable in size, let's say. Let's start there. So you can't really apply this formula directly, meaning, okay, you have the two masses, but what distance are you going to use for the denominator, right? So that's not how you do it. So what do you do then? Well, you make it like a point particle, meaning you just look at some section here, very tiny, a small cross section here, small thickness, like a pillbox, really small, and then use it as your point particle. Let's call it dm. And then you can write the formula for du that corresponds to the gravitational energy due to that dm and m. So now we can apply the formula without any problem. So you will have here m as your first mass, and the second mass dm. Well, what is dm? dm will be the mass contained in that small section, which is of thickness dx, or our coordinate is dy. Let's call it dy. So the thickness here is just dy. So if I multiply the linear mass density, and you're familiar with this from center of mass calculations, if you multiply that density, which is m over L by dy, that's the mass there, the green. So just write it here, m over L times dy. And divide this by the distance between the green mass here, infinitesimal mass, and m, this. So we have x already, and then this part, which is L minus, okay, I need a coordinate y. Let's call this y. Therefore, this becomes L minus y plus x. So in the denominator, I'll need here L minus y plus x. Okay, so take this and then integrate it from y equals 0 to L. Okay, so u is found by adding the contributions of these little parts, means integrate this. So negative g m, capital M, divided by L integration is over dy L minus y plus x. The limits are y equals 0 to y equals L. All right. If you like, call the thing in the denominator, I don't know, y prime, I guess. Y prime will be L minus y plus x. Then dy prime is negative dy. So you will have negative g m over L. Instead of dy, I'm going to write negative dy prime divided by y prime. And the limit is, now when y is 0, y prime is L plus x. And when when y is L, y prime is just x. Okay, two negatives make a positive, then you flip the integral limits. You will have a negative from there, negative g m over L, integral from x to x plus L dy prime over y prime, which is the natural logarithm, negative g m over L ln divided by x. Okay, if you plug in the limit, or u will be equal to negative g mass, the other mass, divided by L ln 1 plus L over x. Okay, so that's the exact formula. Now let's consider the case when you're really far away from the rod, which means consider a large x. X is much greater than L. So this is your rod, but now this point here is really far, okay? 1 kilometer away. At that distance, the pen looks like a point particle, okay? So you know what you expect. You want to go back to a formula that will look like this, right? But let's prove it. So for x really large, what happens? This function, which is, let's say 1 over, I'm not going to use x, let's call it z. If z is really small, this becomes z, all right? In our case, u will be equal to negative g m, capital M over L, and L over x. Okay, using this approximation. Z is like L over x. L's cancel, and indeed u becomes negative g m over x. You totally ignore the length of the object. It just becomes like a point particle. Okay, so you could do the other way around. What if you're really close to the object, all right? And then you can find the approximation. I'll leave that to you for you to work it out. In the other case, when you're really close to the rod, okay? See what you can get. Okay, this was one example. Another one, how about a ring? I saw that problem in your book, in your textbook. Looks something like this. You have a ring. The mass distribution is in the form of a ring. okay? And from the center, if you draw a perpendicular line and place another mass here, M, and the mass here is capital M, and let's say this is X away from the center of the ring. Okay, the mass is only in the ring. Okay, here's where the mass is. The mass will have a radius equal to A, let's say. All right, so how would you find the, okay, I said R, right? Let's not write, let's just write U. How would you find the gravitational potential energy for this system? Again, we're getting the same idea, the M idea. So consider a portion here, really small, infinitesimally small, which is R away from the other mass, R. This R is square root of x squared plus a squared. It's a right triangle, right? And the mass contained here, dm, will be, how are we going to find it? Okay, let me just show you here the side view. All right, so that little section here is what dm is, and that corresponds to an angular increment of d theta, okay, where theta is measured from some arbitrary axis there, but that's d theta. So the arc length here that corresponds to d theta is a times d theta, and if you multiply the density of this object, okay, it's a ring or disc-shaped ring, right? So the density will be an area density, which is total mass times total area. How would you find the area? Well, you know what? This A here, okay. Well, it's a really thin shell. You could solve the version when you have an inner and outer radius as well. That would be a little bit different than this one. So we're really imagining a really thin shell here. So let's use a linear density, okay? Let's just use a linear density. So the total mass, lambda, total mass divided by 2 pi a. That would be the linear density. If you multiply lambda by a d theta, then you get dm. So you'll have m over 2 pi a times a d theta. Okay, so a's go away, and dm is m d theta divided by 2 pi. You can always check this. How? You can integrate that. dm should give you m, right? So the integral will be over theta, and theta goes from 0 to 2 pi. M d theta over 2 pi gives you m, all right? So it checks. Take this dm and now write du that corresponds to it. So negative g times this m here times our dm, which is capital M d theta over 2 pi divided by the distance between the two. So that is square root x squared plus a squared. All you have to do is to integrate this, and there's nothing really dependent on theta. So the integral will just give you a factor of 2 pi. That's all. So du will be equal to negative g m over 2 pi x squared plus, what is the a squared? Integral from 0 to 2 pi d theta. So this integral will get rid of that, and you'll get that expression for u of this system. Negative g m over square root x squared plus a squared, the gravitational potential energy. Now, based on this u, how would you find the force on this mass, say, which you know will be to the left? Okay, now imagine all these contributions along the ring. For each part here, you will have another dm over there. So those two forces will share the same x component, but their y components will cancel. Like this one is attracted this way, but also attracted in that direction. And the y components of these forces will cancel, but the x components will add up. And you have to think about the whole of the ring. For every part, you can find a counterpart over there. If you add them up, the net force is the blue one. It's pointing to the center. And that force in magnitude will be equal to, if you remember this relationship between the conservative force and the gravitational and the potential energy, not just gravitational, but for any potential energy, it's just the gradient of it. And in this case, you can take the derivative with respect to x. So negative d by dx of this. X squared plus a squared. Okay, again, I'll leave the derivative to you, but that's how you find the force based on this potential energy. One more thing before I wrap this up. What if you had multiple masses? How would you find the potential energy? 1, 2, 3. M1, M2, M3. Then you would have to consider the distances between objects. Call this R12, R32, and R13. And then take the pairs now. Negative G, M1, M2 over R12, plus the pair, 2, 3 pair. So G, M2, M3 over R32, and finally the pair M1 and M3. Divided by R13. This will be equal to the gravitational potential energy of the system. Okay, so imagine you already had 2 of them, 1 and 3, and then you take M2 and you bring it all the way from infinity to where it is right now. The amount of work you would do would be equal to that. Okay, so that's the end of this chapter. Till next time.